AI as an agent. There are already many successful AI agents, from games like AlphaGo and Cicero for diplomacy to applications in recommender systems, robotics and drug discovery. What's an agent? In the reinforcement learning textbook, the learner and decision maker is called the agent. In the AI textbook, an agent is anything that can be viewed as perceiving its environment through sensors and acting upon that environment through actuators. For each possible percept sequence, a rational agent should select an action that is expected to maximize its performance measure, given the evidence provided by the percept sequence and whatever built-in knowledge the agent has. Agent is a core concept in AI. The whole fields of reinforcement learning and AI are constructed around agents. Why agents? Building an autonomous learner and decision maker, that is, an agent, is the holy grail of AI. Here we focus on sequential decision making. That is, multiple steps. How to build an agent? There are 3 general methods. First, classical search, optimization or planning methods. Second, data-driven, learning methods. Third, learning plus search, planning methods. AI search methods, operations research, and optimal control are classical search, optimization or planning methods. They are working with a perfect model, or assume so. Deep Blue is a classical example. Data-driven, learning methods include imitation learning, model-free reinforcement learning and model-based reinforcement learning. In reinforcement learning, at each time step, an RL agent receives a state, selects an action, receives a reward, and transitions into a new state. The objective is to maximize long-term reward, or find an optimal policy. RL is a general framework for sequential decision making. Imitation learning includes several methods. One more method to build agents is by integrating learning with search, planning. With a perfect model, simulator or a perfect verifier, we can generate infinite perfect data, with a prominent example of AlphaGo. Without a model, usually, we estimate a model. Note, we need to deal with the estimation error. Learning plus search is promising for AI, including LLMs. AlphaGo is the first program to defeat a world champion in the game of Go. It set a landmark in AI. The key techniques of AlphaGo are deep learning, reinforcement learning, policy iteration, self-play and Monte Carlo tree search, MCTS. The details of AlphaGo series are very involved. Stay tuned for explanation in a later video. Lessons from AlphaGo, AlphaGo 0, Alpha 0, perfect game rules so that perfect model so that infinite high quality or perfect data. It follows trial and error, with general policy iteration, self-play and it iteratively improving the policy. Experiments results show that imitation learning is far from enough for the game of Go. AlphaGo and previous programs like Crazy Stone use expert moves as training data. However, the ELO scores are much lower than AlphaGo trained with reinforcement learning and MCTS. In the figure, AlphaGo 0 achieves the highest ELO score. It is trained without any expert moves. Sergey Levine talks about imitation learning is not enough in a general sense. Natural language processing, NLP, is very complex. For most NLP problems, there are no objective objectives. Performance metrics like Blue, Rouge and Perplexity are heuristics, or best efforts. Multi-objective, multi-constraint by nature, for example, accuracy and human value alignment. It is very hard, if not impossible, to build a perfect model. An auto-regressive language model specifies the conditional probability distribution of next token, given previous tokens. The transformer is the backbone of large language models and foundation models. GPT stands for Generative Pre-trained Transformer, Supervised Fine-Tuning, SFT, and Reinforcement Learning from Human Feedback, RLHF, are imitation learning. GPT with next token prediction may behave like imitation learning, so that it learns policies or strategies in the training data, to some extent. For example, planning a trip. Imitation learning may be helpful, or even better than reinforcement learning, for some NLP problems, including LLMs, especially those without objective objectives. Statistical model often provides little insight beyond modeling associations between epiphenomena. Is a perfect world model enough? Not really. For example, although chess has the rule, It takes computer scientists several decades to develop Deep Blue and AlphaZero. Each problem requires a world model. This is a challenge for both RL and LLMs. We may not rely on the implicit world models in an LLM. For example, Othello GPT is still struggling with legal moves. There is a simulation to reality gap between a learned and the real models. We need to bridge this gap and handle approximation error. Ground truth in the loop is a basic scientific principle. We need trustworthy training data, dependable evaluation feedback, and reliable world model or verifier. Examples of ground truth signals: game scores, code interpreter, compiler. Examples: unit test results, maths verifier, problem solutions, human, especially expert feedback. Note: LLMs are not ground truth, yet. Will synthetic data help? It depends. It helps if there is a perfect world model, a perfect simulator, like a game rule or a physics law, or there is a perfect verifier. Otherwise, it is unclear, or it may be harmful. Constitutional AI, harmlessness from AI feedback. That is, RL from AI feedback, RLAIF. Note: rules for a language won't be perfect. There are self-generation of data, self-evaluation of results, and self-improvement of the model. Many such self-something approaches. It is actually information perpetual motion machine, unless with reliable, external, information. Self-play in AlphaGo is different, since perfect game rule can generate perfect feedback. In general, such self-something approaches may be a decent start, however, it is limited by the LLM. Model-based RL updates the world model iteratively with real experience from the environment. AlphaZero works with discrete games. MIT professor Dmitry Burtskas published a book titled Lessons from AlphaZero for Optimal, Model Predictive, and Adaptive Control, showing influence of AlphaZero in continuous decision makings. A recap: 3 general methods: classical search, optimization or planning methods, data-driven, learning methods, and learning plus search, planning methods. Google DeepMind published a paper titled Levels of AGI, Operationalizing Progress on the Path to AGI, discussing levels of AGI and autonomy. 6 levels of AGI: no AI, emerging, competent, expert, virtuoso, superhuman. With respect to performance, depth, and generality, width, that is, narrow or general. 6 levels of autonomy: no AI, AI as a tool, AI as a consultant, AI as a collaborator, AI as an expert, AI as an agent. Straightforward implications. Current LLMs are far from being superhuman AGI. AI as an agent are far from being ready. LLM's ability to generate executable plans autonomously is rather limited. However, LLMs show promise for heuristic guidance. Transformers have limitations on compositionality, like solving multi-digit multiplication problems. 3 factors influence LLM accuracy: the probability of the task to be performed, the probability of the target output, and the probability of the provided input. AI practitioners should be careful about using LLMs in low probability situations. AI aims for optimality. Most LLMs are pre-trained without optimizing for downstream tasks. Most works utilizing LLMs focus on feasibility and correctness. There is an optimality gap to bridge. Building agents with LLMs trained from text is like learning to swim by only reading books. LLMs-based agents. There are fundamental issues with a fixed, imperfect LLM. Most current LLMs do not incorporate agency. Autoregressive LLMs are lacking of planning abilities. Methods like React and Retrieval Augmented Generation, RAG, may mitigate but not eliminate such issues. Desirable to train agency, planning during fine-tuning or pre-training. LLMs-based agents are still an open research problem. VCs and entrepreneurs, watch out. What to do then? Iterative improvements from reliable feedback. Most, if not all, successful systems make iterative improvements from reliable feedback, from gradient descent to policy iteration to evolution of our humankind. Let's talk about the state of the art. Methods to improve LLMs. in different angles, pre-training, fine-tuning, prompt engineering, feedback and language models. BERT, T5 and GPT are well-known pre-trained models. There are also models pre-trained with planning capacity, like GPT-F for maths, AlphaCode for coding, Web Agent for web navigation, and Gato and Adaptive Agent for general planning. DeepMind trained an adaptive RL agent at scale, leading to a general in-context learning algorithm. It can adapt to open-ended novel embodied 3D problems as quickly as humans. Competition-level code generation with AlphaCode. And AlphaCode 2 was released with Gemini. GPT-F is an automated prover and proof assistant, a real-world web agent with a fixed LLM for grounded code generation and a newly introduced, domain expert pre-trained language model for task planning and conditional HTML summarization. Besides supervised fine-tuning, SFT, and reinforcement learning from human feedback, RLHF, there are more and more studies on fine-tuning methods. Most works are about prompt engineering, either open loop, or closed loop with fixed LLMs. There are works following the approach of closed loop feedback with iterative improvements of language models. This would be the ultimate solution, human-level play in the game of diplomacy by combining language models with strategic reasoning. Code RL, mastering code generation through pre-trained models and deep reinforcement learning. Planning with large language models for code generation. Lean Dojo, theorem proving with retrieval augmented language models. DT Solver, automated theorem proving with dynamic tree sampling guided by proof level value function. Offline RL for natural language generation with implicit language queue learning. Retroformer, retrospective large language agents with policy gradient optimization. Socially situated AI enables learning from human interaction. Modularity, and small LLMs facilitate iterative improvements from feedback. Common sense in society, specialists are usually preferred to generalists, and the society follows the principle of division of labor and cooperation. AGI with a single model is a wrong goal, based on two basic principles in optimization. First, multi-objective optimization usually will not optimize all objectives. Second, the more and the tighter constraints, the less chance to find a feasible solution. If smaller, cheaper, yet similar, or even better, then why not? We thus propose a specialized, modular and small framework, following iterative improvement from reliable feedback. The key requirements are reliable data, feedback, dependable world model, verifier, and capable architecture, algorithm. Modules 0 to N send decisions to and receive feedback from other modules, tools, APIs, and the task. Module 0 serves as a coordinator. Modules can interact and learn from each other. From RL's perspective, a learning module is an agent, and the rest is its environment. Let's talk about more caveats. Will compression lead to intelligence? For AlphaGo, the policy would be the most concise info. However, without AlphaGo, GPT with next token prediction won't find a superhuman policy, almost surely. Likely new mechanisms are needed for agency in general. Transformers are Turing complete. Is AGI attainable soon? Many programming languages, like Python, are also Turing complete. AI is different from IT. An IT system is usually transparent, targeting what you see is what you get, so that a problem may be fixed. In an AI system, a problem may be hard to fix, especially for black box systems. It is even harder for agents with multiple steps. There is hidden technical debt in machine learning systems. Technical debt is the long-term costs that accumulate when expedient but suboptimal decisions are made in the short term. ML systems incur massive hidden costs at the system level, beyond the basic code complexity issues of traditional software systems. There are many feedback loops in the workflow software engineering for machine learning. Data cascades are opaque and protracted, with multiplied, negative impacts. Cascades are triggered in the upstream, for example, data collection, and have impacts on the downstream, for example, model deployment. A foundation model is any model that is trained on broad data, generally using self-supervision at scale, that can be adapted, for example, fine-tuned, to a wide range of downstream tasks. Tons of attempts of direct applications of foundation models, For example, ChatGPT with prompts. Forget the very founding mission. The performance of GPT-4 and GPT-3.5 varies substantially over time, and sometimes for the worse. Generative agents, interactive simulacra of human behavior. With an imperfect model, human simulator, without a viable approach to improve the model, what kinds of worlds this may generate, it is unclear if the current LLMs are good enough to be the foundation. Not mention the OS or the iPhone metaphor. Now we take an outlook. Grounding, agency and interaction are indispensable for sound and solid LLMs. A language describes the physical world and facilitates the social interactions. We can't learn language from a radio, internet, from a television, or by ourselves. 5 levels of world scopes: small-scale corpus, our past, for corpora and representations; large-scale internet, most of current NLP, for the written world; perception, multimodal NLP, for the world of sights and sounds; embodiment and action for interaction with physical world, and social world for interaction with human society. The embodiment hypothesis is the idea that intelligence emerges in the interaction of an agent with an environment and as a result of sensory-motor activity. 6 lessons from baby's development of embodied cognition: be multimodal, be incremental, be physical, explore, be social, and use language. DeepMind Gemini is multimodality native. OpenAI GPT-4v stitches texts with images. They have not incorporated embodiment and interaction. They are not agent native yet. Sensory motor experience is the sensations and actions of an agent's ordinary interaction with the world. Over AI's 7 decades, experience has played an increasing role for AI to be more grounded, learnable and scalable. Rich Sutton proposes the common model of the intelligent agent, a perspective on the decision maker that is substantive and widely held, across psychology, AI, economics, control theory, and neuroscience. Such an integration of experience and model leads to an integration of empiricism and rationalism and an integration of connectionism and symbolism. This will lead to sound and solid grounding and agency. Yann LeCun proposes a path towards autonomous machine intelligence. It is essentially the same as the reinforcement learning model proposed by Rich Sutton. Note the world is missing in the figure from a NER IPS 2023 tutorial on language models meet world models. Rich Sutton states in the blog The Bitter Lesson, the 2 methods that seem to scale arbitrarily are search and learning. He also highlights the importance of meta methods. Sergey Levine states that, data without optimization does not allow us to solve problems in new ways. And optimization without data is hard to apply to the real world outside of simulators. Read also blogs by Rodney Brooks and Leslie Kaelbeling. Reinforcement learning unifies classical computing methods like dynamic programming, Monte Carlo, and search. Monte Carlo tree search, MCTS, and evolutionary methods, genetic programming, etc. are relevant. The history of AI chess tells us that there were lots of explorations before Alpha 0. The history of AI tells us, integration of learning and search is powerful. The history of computing, from ENIAC to iPhone, tells us that LLM calls for innovations, including for transformers. Based on the principle of ground truth in the loop, the purpose of AI aims for optimality, and the purpose of AI adapts to humans. To respect the premise of general intelligence with a single model is approximation. The premise of grounding, interaction and agency are indispensable for intelligence, and the purpose to bridge them to real gap. We follow the principle of iterative improvements from reliable feedback, to build specialized, modular, small models, benefiting from the power of the integration of learning and search. Here is a proposal for problems with ground truth signals like maths and coding, with learning and search, with ideas from AlphaGo, augmented with GPT. Stay tuned for more details in a later video. Here is a concrete example: mathematical discoveries from program search with large language models. Note, no free lunch. Fun Search currently works best for problems having the following characteristics: availability of an efficient evaluator, a rich scoring feedback quantifying the improvements, as opposed to a binary signal, and ability to provide a skeleton with an isolated part to be evolved. Let's build AI agents together. Let's follow the general framework of iterative improvements from reliable feedback. It is friendly to small players, academia, small startups, even individuals. It benefits from decentralization, open source, and wisdom of the crowd.